All right, let's talk about one of the absolute cornerstones of computer science, graph traversal. Seriously, understanding this is like getting a key that unlocks a ton of problems, everything from how your GPS works to how social networks are analyzed.
You ever pull out your phone, pop in an address, and wonder how it finds a route? Well, that's graph traversal in action. Your phone is basically looking at a giant map, which is just a graph, right? And it's systematically exploring it to get you from A to B. And notice that I said any route, not necessarily the fastest route. That little distinction is a perfect sneak peek into the two methods we're about to break down.
So, what is graph traversal? Officially, it's just the process of visiting every single node in a graph, but in a very organized way, and you only visit each one once. The two big players, the workhorse algorithms for this, are depth-first search, or DFS, and breadth-first search, which we call BFS. And by the end of this, you're going to know them both inside and out.
Here's our game plan. We're going to dive deep with DFS, then spread out wide with BFS. After that, we'll look at how they solve real-world problems, and then we'll wrap it all up with a summary that's tailor-made to help you ace your exams. Sound good? Let's get into it.
First up, depth-first search. Now, the absolute best way to get your head around DFS is to think of yourself as a maze explorer. You get to a fork in the road, you pick a path, and you go down that path as far as you possibly can. You don't even think about the other paths. Only when you hit a dead end do you turn around, go back to the last choice you made, and then you try a different path.
And here's the textbook definition you'll want to remember. DFS is an algorithm that explores as far as it can along each branch before it has to backtrack. It's all about that single-minded focus, going deep down one path at a time. Okay, let's watch it in action. We're starting at node 1. DFS doesn't hesitate. It just picks a path and dives right in. See how it follows that edge straight to its neighbor, node 2? That's our first step deep into this graph. Now from node 2, do we look around? Nope, we keep plunging deeper. First to node 3, and then from there all the way to node 5. But now we're at node 5 and, it's only neighbors. 2 and 3 are nodes we've already seen. That's it. We've hit a wall, a dead end. So what happens at a dead end? This is the key part. We backtrack. The algorithm literally traces its steps back, going from 5, back through 3, back to 2, searching for the last place it had another option. And in this case, that takes us all the way back to where we started, node 1. So, we're back at node 1. The algorithm finds that last path we haven't tried yet, the one leading to node 4. It takes it, and that's it. Every node we can reach has now been visited. DFS is done. Now, what does the code for this look like? It's usually done with recursion, and it's surprisingly simple. The magic is right here. The DFS function calls itself for its neighbors. That's what creates the diving deep behavior. And the best part? The system's function call stack automatically handles all that backtracking for us. It's pretty neat. Okay, for your exam, these are the facts you need to burn into your brain. The core engine is a stack, which recursion gives you for free. The time complexity is O of n plus m, because we touch every node and every edge just once. And here's the rookie mistake to avoid, forgetting to check if you've already visited a node. If you forget that, on a graph with a cycle, you'll get stuck in an infinite loop forever. You don't want to do that. All right, let's totally switch gears and talk about our second algorithm, breadth-first search. Now, if DFS was the focused maze explorer, BFS is completely different. Think of it like dropping a pebble into a pond. It explores outwards from the start in perfect, ever-expanding circles, or ripples. And the formal definition says exactly that. BFS explores all of the neighbor nodes at the current level before moving on to any nodes at the next deeper level. No diving in, just methodical, layer-by-layer exploration. So let's see how this looks. We start at node 1 again, but this time, instead of picking one path, BFS visits all of its immediate neighbors first. So it goes to node 2 and node 4. That's our first ripple, which we call level 1. Now that we've finished level 1, we move out to the next ripple. We take the nodes from that first level, starting here with node 2, and we visit all of its unvisited neighbors. And as you can see, that gets us to nodes 3 and 5, which form our new level 2. And we just keep going. Finally, we process the nodes at level 2. From there, we can see their unvisited neighbor is node 6. That forms level 3. And just like that, every reachable node has been visited, one perfect layer at a time. So what's the secret sauce in the code that creates these ripples? It's a simple data structure called a queue. Think of it like a line at a store. First one in is the first one out. We add our start node to the queue. Then, in a loop, we pull the node from the front of the line, process it, and add all its new neighbors to the back of the line. This simple trick forces the algorithm to finish one whole level before it can even start the next. Okay, exam facts for BFS. The core mechanism is a queue. Time complexity is the same as DFS, O of n plus m. But here it is, the killer feature. Because BFS explores level by level, it is absolutely guaranteed to find the shortest path, in terms of the number of edges between the start node and any other node. This is a huge deal, and it's a classic exam question. Remember that. So we've got the theory down, but where does the rubber meet the road? Let's check out a couple of classic problems you can solve with these traversals. These are exactly the kinds of application questions you're likely to see on a test. First up, checking if a graph is fully connected. How do you do it? It's actually really simple. You just pick any node to start from and run either DFS or BFS. When it's done, you just count how many nodes you visited. If that count is less than the total number of nodes in the graph, well then you know it's disconnected. You can see here, if we start on the left, we'll never reach the nodes on the right. Easy proof. Here's another classic, checking if a graph is bipartite. Fancy word, simple idea. Can you color the graph with just two colors so that no two nodes connected by an edge have the same color? BFS is perfect for this. You color your start node blue, then color all its neighbors red, then all their neighbors blue, and so on, alternating level by level. If you ever find an edge, like this one right here, that connects two nodes of the same color, you've got your answer. The graph is not bipartite. All right, let's bring this all home. Time to wrap things up with the final summary. This is definitely the part you'll want to screenshot for your study notes. And here it is, the ultimate cheat sheet. Let's break it down. Data structure. DFS uses a stack, usually through recursion. BFS uses a queue. This is the most important difference because it leads to the next point. Does it find the shortest path? For DFS, no. For BFS, yes, absolutely, in an unweighted graph. And that dictates their use cases. DFS is great for just finding a path, like in a maze. But if you need the shortest path, BFS is your go-to every time. We've covered a ton of ground, but honestly, this is just scratching the surface. Now that you have these powerful tools in your belt, you can start thinking about much bigger problems. How do you figure out the degrees of separation on Facebook? How does information get routed efficiently across the internet? The answers to all these complex questions, they all start right here, with the traversal methods we've just mastered.